anybody who can't make it can catch up, or you can go back and check on something that's said. Thank you to those who have submitted their assignment. Quite a few of you have done that already, and I must say I've not marked. Oh, I marked a few of them, and I had a quick look at the others, and really good stuff. So you're all getting the hang of where to find that information about a particular barrier product and its advantages and disadvantages, and you're understanding the different approvals or what it's been tested under and the like. So thank you for that. Anybody who hasn't quite got to that yet, please have a go at that. It shouldn't take you too long. And at the end of today's session, you've got another quiz to do, and that's the final thing that you actually have to submit as part of the this session. This course. And next session is where we're going to go through some real-world examples, lots of pictures of barrier installations that have gone wrong, or things that are good, and the like. And I'll remind you that that's your opportunity to provide a specific project example that you might have, that you would like Jamie, myself, to make some commentary about. So if you've got a challenging situation or a design that you want to have a look at, or there's a particular question or product you're interested in, send that through. You can send it through via the chat now, or the Q&A, or you could send through some plans via email, or just some coordinates or a street view location, and we will allocate some time at the end of next session, Thursday session, to go through that and to have a chat about it. And you'll have the ability to to talk if you want, and explain the issue or what you're thinking around it, and Jamie and I will make commentary on that. Okay, already getting a few ideas come in. That's good. We'll add those as topics for our discussion, but please send those through. So today's session, Jamie's going to go into a bit more detail about some of the design thinking and calculations and way you work out the length of barriers that are required, or other offsets and features like that. So it's a real run through the design steps, and as I mentioned earlier, Jamie's certainly done a lot of this design work in his time, and he's a perfect person to do this. I'll be in the background collecting your questions, and I'll be feeding those to Jamie as we go. So please, as you think of them, type them in. I've got a little quiz along the way, and I will finish it off by talking to you about motorcyclists and barrier systems in the last 15 minutes or so. But if there's no particular questions, got a few more things have come in for us to talk about next week, which is good. I'm going to hand it over to you, Jamie.
Can you just enable my screen sharing, please, Ken?
Will do. Yeah, sorry about that. That should be good now, I think. Yep, there we go. See your screen. And yep, that's in the correct view. So I'll slip into the background and leave it with Jamie, but please pop those questions into the Q&A or the chat, and I'll feed them through to Jamie. Thank you.
Great, thanks, Ken. Good afternoon, everyone. So today I'd like to talk about the barrier design process. We've talked about when we might choose to install a barrier, when one might provide a safety benefit, and Evan's talked to you about the different products that are available and the steps that they're put through to be accepted for use. Today I'd like to discuss a few of the key design steps and considerations when it comes to designing a barrier installation. There's lots of guidance available to us. We've talked about the new revision of Part 6 of the Austroads Guides, which is the primary reference guide in all jurisdictions. Each state has its own supplement to that guide. They do vary in terms of their detail and size, I suppose. The Victorian supplement's quite a lengthy document. Others are relatively short and put the onus on the designer to make to make more of the decisions, I suppose, in accordance with the guide. Each jurisdiction has its own set of standard drawings, sometimes referred to as guideline drawings. In Victoria in particular, there's a lot of specific guidance available. Each state has its own list of accepted products, which generally align with the Austroads acceptance conditions. In Victoria, they've got a suite of design notes to help you design with wire rope barriers, with guard fence systems, continuous barrier applications, and median applications. So there's lots of stuff there. DOT in Victoria has recognised recently that they probably should consolidate some of this guidance. So there's a piece of work in progress at the minute to combine these 3 road design notes. The information from those will appear in a design commentary. So that'll be a road design note that brings together elements of all 3 of these documents. Some of that information will shift into the VicRoads supplement to the Austroads guide. All of these Victoria-specific documents can be found at the VicRoads website, and you can see the link there. Similarly, in the other states, you can refer to your relevant department's website for the appropriate guidance. It is sometimes a good idea to look to the product suppliers' websites. You can get more information, some more detailed and specific information about the performance of a particular product, how it's been crash tested, some perhaps more specific information on deflection and the arrangement of that system and its variants. So the first step in designing a barrier is to really think about what the barrier is intended to do. What's its function or its location? Is it to be installed at the roadside? And if it is at the roadside, its primary function is to shield the occupants of errant vehicles against that run-off road crash. So a vehicle might depart the road, strike a tree, or roll over, or the like. So in those cases, we generally would seek to provide the most flexible barrier system that we could. If we're at a bridge or a median where there is perhaps a greater consequence if the vehicle penetrates that barrier and ends up on the road or the waterway below, or enters into oncoming traffic, which might particularly be an issue in a high-speed urban freeway environment, for instance, and we might beef things up to concrete. Wherever we do have a barrier in a median, it must be the barrier must be safe to be struck on either side, whereas at the roadside, we'd only expect the barrier to be struck on one side. And at work sites, we have a whole different suite of products available to us. Typically, we're dealing with lower speed environments, and the main function of the barrier is to shield those workers working behind the temporary barriers. So think about the location and the function of your barrier and what is its primary purpose. And if there are secondary consequences that may occur, look to beef up your containment level, as we typically do at bridges. There are those 3 categories of longitudinal barrier, and we'll go through the ins and outs of each of those, but it is important as a designer to know the pros and cons of the different systems that are at your disposal. So we've got rigid or bridge barriers, semi-rigid barriers, which are our typical public domain guard fence systems, and our flexible products. Any of those systems needs an appropriate end treatment. That might be in the form of an end terminal that's integrated with the system, or perhaps it's a standalone crash cushion or impact attenuator, which you might see at the end of a concrete system, a rigid system, or perhaps located around a pole, as in the case of a Raptor crash cushion, which probably falls into that point protector category. We're mostly talking about permanent installations today, but basically the same principles apply to any installation, permanent or temporary. But we are dealing with a different suite of products and typically a different barrier function and different speed environments. A rigid barrier might look like this. Typically they are a concrete system, perhaps with a steel extension. Depending on the vehicles that we are intending to contain, we might provide that steel extension to contain those vehicles with a higher centre of gravity. So these barriers don't deflect by very much at all, in fact, next to nothing. And because of that, they aren't particularly forgiving on the occupants of the errant vehicles. So that lack of deflection is good in terms of maintenance requirements, because you typically don't need to attend to the barrier after it's been struck. It will incur little or no damage and it will stand to live another day. But we do see some more serious outcomes when crashes occur with these type of systems. And that's especially the case where we have where higher impact angle crashes are possible with these barriers. So if we have a fairly contained road environment where there's not that opportunity to work up a severe exit angle, there's no issue with a rigid system. And a typical application would be on either side of a high-speed urban freeway, for instance. As you can see there, that's the Balti Bridge in Melbourne. So you'd be hard-pressed probably to work up say a 25-degree impact angle at significant speed with one of those barriers due to the limited width available and the fact that the alignment is fairly straight, or its geometry is pretty generous. They don't deflect much, they don't damage much typically. They can contain those larger vehicles. You can engineer a rigid barrier system to contain as large a vehicle as you like, and they typically fall into those higher containment level categories of TL4 and above. But you do need to be mindful of the potential for higher impact severity where you're using a rigid system. So rigid systems, therefore, are typically used at those locations where there is a secondary possibility. A vehicle that penetrates a barrier might strike a piece of critical infrastructure, or there might be a school or some other vulnerable location that's located adjacent to the road that we want to prevent a large vehicle in particular from entering. Stepping down in terms of rigidity, we've got the semi-rigid category. So in the past, we've seen a lot of public domain semi-rigid barrier, your type B guard fence or G4 guard fence and the like, which are pictured on the left. On the right, we've got a tri-beam barrier, and there are a number of proprietary tri-beam systems available. They're a higher containment level barrier than your typical public domain guard fence, but they all fall into that semi-rigid category. These systems deflect by a bit, perhaps in the order of 0.5 metre, 1 metre, which does mean that they're somewhat forgiving on the occupants of the errant vehicles. They do sustain some damage when they're struck, but typically that damage is fairly localised, and therefore they can remain serviceable after an impact. Damage might be limited to perhaps a 10 metre section or something like that. There might be a bit of damage to the rail, but the barrier typically is still largely intact, except in the case of some particularly high energy impacts. Semi-rigid systems can be, of all the systems, probably the most easily applied in constrained locations. You can use some fairly short lengths, you can curve them fairly tightly. So that's certainly an advantage of these systems over something like a wire rope barrier. In the flexible barrier category, we do have wire rope barriers, as you can see there on the left, and the newer breed on the right being the flexible W-beam systems, sometimes referred to as a weak post W-beam system. Each of these systems deflects by a fair bit, and therefore is really quite forgiving on the occupants of the impacting vehicle. They sustain damage over a longer length when they're impacted, and that's particularly the case for wire rope. Typically, quite a number of posts are knocked down. The cable tension can even be lost, in which case the barrier is ineffective until it's repaired. So wire rope systems typically do have a greater maintenance requirement and need to be attended to more quickly if they are struck. And for that reason, they're often not preferred in locations where we would expect frequent impacts. And the bottom dot point there particularly applies to wire rope again. It is the most difficult system to apply in constrained locations, and that's because of its minimum length requirements. We'll talk a bit more about that shortly. And also some limitations on the way it can be curved, both horizontally and vertically. I encourage any questions as we go through, keeping in mind that tomorrow, or Thursday rather, we will have time to go through any specific examples that you have as well. A little bit of safety barrier philosophy, which is probably a bit of a rehash from last week. We should only install a barrier where it will reduce the risk associated with the roadside. There has been a shift in thinking there. It used to be the case that installing a barrier is probably well down the list of potential treatments, but it's been recognised now that installing a barrier, especially a flexible type barrier, is probably the safest thing you can do in a high-speed environment to eliminate the risk associated with a roadside. AASHTO talks about whole of life cost, and this is often something that's debated, and the flexible W-beam systems really do have an advantage in this area as compared to a wire rope, and are becoming more and more popular for that reason. We should use the most flexible system that we can, subject to the constraints of the site and our design requirements. So with that in mind, a wire rope system should be the first barrier that you look to. Then you need to think about, are there other things that might mean that we need to beef up our containment level? Are there constraints at the site that mean that we can't install wire rope and we need to step down the list, going to flexible W-beam, semi-rigid, and so on? And in all of this, we need to keep in mind the speeds that we have at our site and the likely impact angle. Things will affect the impact severity of any crash, perhaps the likelihood of barrier penetration, and that can feed into your choice of system. Now, the Austroads Guide, Part 6, does provide a process for barrier design. It has quite a lengthy flow chart with something in the order of 16 steps, and it's a bit of an iterative process. I haven't reproduced that here, but I have tried to capture some of the steps or the considerations that I find most important. I wouldn't expect you or anyone to follow that process from end to end. I never have, but the good thing about it is that it does capture all the important considerations. So a bit of a summary of some of the key things you need to think about. Identify the hazard. So what is your hazard? Where is it in relation to the road? We use this term protected width. That's the width of roadside that we need to protect to adequately shield the occupants of errant vehicles from the hazard that we've identified. That feeds into how long does our barrier need to be to shield that hazard. We use that term length of need, and we'll go into these in a bit more detail shortly. We then need to locate our barrier in relation to the roadway. So we need to be thinking about all of these cross-section elements, traffic lanes, where is our edge line, how wide is our shoulder, is there a curb, where is our hinge point and how far from the edge line. So get out on site. You can't have too many measurements when you're looking to design a barrier. We need to be mindful of allowable batter slopes for installing barriers. Think about run out areas. I think we've mentioned them, but we'll go into a bit more detail on that shortly. That may influence your barrier design. You need to think about other things that are happening at the roadside. There might be existing barriers, or there might be other hazards that might warrant a different type of barrier that we need to transition to, and perhaps directly transition to or overlap with. So we need to think about all of these things in our roadside. And we need to choose a barrier. We might have it in our minds that we want to go with the most flexible system, perhaps a wire rope, but we realise then that there are constraints that mean that we need to step down the list. And we need to design an appropriate terminal for our barrier. So these are all the details that we need to work out through the process and will help us arrive at a suitable barrier design. Now, it really is quite an iterative process sometimes. There are lots of desirable things that we want to do in terms of choice of product, offset of barrier from the edge of the road, but typically in retrofit situations especially, we find that we can't do all of those things. So we have to make some compromises in terms of the type of barrier that we use, where it's located, and so on. I mentioned retrofits. There are two distinct cases when it comes to barrier designs, and one is the retrofit. And here is an example drawing for a retrofit barrier design. Don't worry too much about the notation that's being used there. That's a shorthand that Vic Roads has used in the past that basically describes the barrier in terms of its location relative to the road and how long it is, barrier type, and so on. In a retrofit, we typically don't have the luxury of providing generous barrier offsets. So we're basically doing the best that we can within the constraints of the site. We also don't have survey information typically, and we will therefore present our design on an aerial photo base often. It is critical when you're designing a retrofit project to identify some feature out on site that can be used as a reference point. And you can see here we've got an RP reference point, which is a tree located 4.7 metres from the edge line. The information in this little block of text here describes how that barrier ought to be set out about that reference point. So that's what we might be looking at with a retrofit situation. The other case is either a new road design project or a significant upgrade. And this is an example drawing where we have survey information, we have other road design drawings and elements that our barriers need to integrate with. And typically your barrier design would appear on a plan like an alignment plan. The amount of information that's shown regarding this barrier here is fairly minimal. You can see some changes noted there at the start and end of the barrier. In fact, it's not quite the start and end, but it's the point of need. And we have terminals before and after those points of need. The offset from the road is not noted, but you could scale that off the drawing, or you could interrogate the CAD drawing to work out that information.
Amy, there was just a question in here asking you to explain what protected width is, but I think one of your future slides goes into that in quite a bit of detail, doesn't it?
It does, yep. So that might be coming up fairly soon, I think.
Yep, but it is certainly, and clarification to the question here, it's certainly different to clear zone. So but Jamie will explain exactly what protected width is shortly.
And another drawing of a retrofit project. This was a continuous barrier design job on a freeway near Melbourne. So the art of continuous barrier design often comes down to where do you locate your breaks-in barrier. How do you coordinate those with access points for maintenance or gateways and so on? What barrier offset do you adopt, and what system do you go with? Beyond that, there's sort of relatively few decisions as compared to a retrofit, where you're sort of concerned about how long does it need to be, deflection, achieving deflection to the hazards that are closest to the road, and these type of things. Here we go with protected width. So length of need is essentially how long does your barrier need to be to shield the particular hazard that you've identified. And it depends on a number of things, and the first of those is the protected width. You can see the protected width noted here. It's that distance from the edge of your roadway, your edge line if you have one, or the edge of seal if there's no edge line, or perhaps if it's an unsealed road, it's sort of the edge of the travelled way. It's the distance from the edge of your road to the furthest part of the hazard from the road. So it's that entire width that you want to shield an errant vehicle from entering. So I hope that makes sense. It's not the width to the nearest part of the hazard. It also needs to take into account how wide or big the hazard is, so that the barrier shields every part of that hazard. So your protected width feeds into your length of need determination. How close to the road your barrier is also affects your length of need. You can see here we've got a barrier located quite close to the edge of the road, in which case it needs to be fairly long to shield this errant vehicle run-out line. If the barrier was nearer to the hazard, here for instance, it could be much shorter and still offer the same level of protection. There might be other concerns that you have with perhaps rollover before a vehicle strikes that barrier, but to shield that particular hazard in its own right, you could get away with a fairly short barrier. Your operating speed affects your length of need as well. The faster your operating speeds are, the longer a barrier needs to be typically. If a barrier is flared, we can reduce our length of need, or we can at least ensure that our barrier is as effective as it can be in terms of shielding that hazard. We might have a constraint here, perhaps a driveway or something, that means that we perhaps can't make the barrier as long as we'd like, but we might want to flare it away. You can see a flared terminal here, and that just serves to cut out that run out line just a little bit sooner and offer better protection to that hazard.
Amy, you might want to answer this now, or we might want to just hold it to the end. But the questions come in about a creek or a something that is, a very long hazard. So I'll work that in.
Yeah, no, it's a great question. So the image here shows a discrete hazard at a certain distance, and we're just looking to shield it. You might have something like a creek or a waterway that sort of extends, continuously or for quite some distance away from the road. If that's the case, you have to make a decision on a protected width to adopt. How much of that waterway do you try and shield? And the common approach in the past has been to adopt the appropriate clear zone as your protected width. So that continues to be probably one use of the clear zone approach, where you've got those, your hazard is a creek or a river or something like that. you might assume a protected width equal to the distance between the edge of the road and the property boundary would be another way to go about it. But obviously we can't shield that creek or river forever, and we need to draw the line somewhere. So just to summarise, your length of need is that distance required to shield this hazard from the errant vehicle. And it's measured between the barrier's point of redirection, and which is here, and the first part of that hazard. So you'll recall that not the entire length of our barrier or our terminal is effective in redirecting an errant vehicle. Each system has a gating portion, a portion that's intended to not contain that vehicle, and a vehicle that impacts this part is likely to enter the roadside still. So it's important to think about the point of redirection, not the very start of the barrier. In Victoria, you can refer to these guideline drawings for some guidance on how long your barrier needs to be. So we might have a one-way roadway or a two-way roadway. If it's a one-way roadway, we're only concerned about shielding a hazard for one direction of travel. If it's a two-way situation, we need to think about the length of need from both directions. So our total length of need would include both of those elements plus the length of the hazard, as you can see there. And your total barrier length is your total length of need plus a bit more. You need to think about these bits of your terminal, or it might be the entire terminal length in the case of wire ropes, which are beyond your points of redirection. I hope that makes sense. Now, I do want to point out that there are two methods that are used for determining lengths of need. They're both described in the Austroads guide. One is called the run-out length method. That is what we use in Victoria. And this guideline drawing uses the run-out length method for determining lengths for barriers. The alternative method is referred to as the angle of departure method, and that's used by New South Wales and some other states. The angle of departure method adopts a fixed run-out angle, which is based on the operating speeds at the site. So it might be a 3-degree run-out angle relative to the alignment of the road. The run-out length method, however, does not use a fixed run-out angle. It basically looks to provide a corridor for deceleration. We provide a barrier that's long enough to prevent a vehicle from getting in behind the barrier and continuing with enough speed to reach the hazard that we're shielding, or at least strike it with significant speed or enough speed for a severe outcome. So it uses some formulae that are provided in the Austroads guide, and this VicRoads guideline drawing has done some of the work. It's applied those formulas for different situations. It's probably a bit hard to make out there. Some of you might be familiar with this drawing. You need to determine your protected width, have assumed a barrier offset relative to the edge line, and know your operating speed. And if you have those three things, you can look to these tables and select the length of need that you require. Now, another thing that I will point out with the run-out length method is that with the recent update of Part 6, run-out lengths have reduced in length significantly. And this drawing is no longer current. It has not been updated to reflect those reductions in length, and they are significant. They're sort of in the order of 30%. reduction. So I encourage you to look to the new Part 6. There is a table of run-out length values given in that table. And you would need to apply the formulas using those lengths rather than look to this table. Of course, if you applied this table, you're being conservative and you're providing a longer length than you need. But under the current guidance, you can get away with some shorter lengths using the run-out length method.
Jamie, can you just jump back a couple of slides and point out, one more slide back, So the flared terminal, no, forward one, that the bit at the bottom, there's a bit of confusion, I think, about the flared grate, so the gating redirective energy absorbing terminal. So it might be, because you've got a straight one and a flared one, it kind of looks like a V-like thing.
Yeah.
Do you want to
okay.
That?
Yeah. So there are two options here. You can continue your barrier on a straight alignment with a straight terminal, or you can flare it. You can kick the barrier around and flare the terminal away from the road by a little bit. You don't want to flare it away by too much, because that opens up the possibility of some more severe impact angles. So you can flare a terminal by just kinking around the terminal itself. The entire terminal needs to be straight, but you can basically kink your rail between the terminal and your longitudinal barrier, or introduce a short radius at the transition here to flare the terminal away. Or you might provide a radius and then a straight section of barrier, and then your terminal, which would help get the terminal even further away from the road. And that's sometimes referred to as this line A treatment. That's what line A means. You've got a straight section, and then a radius, and a straight, if that makes some sense.
Well, I'll chuck a prize out there for the person that can tell me what the acronym GREAT stands for. We've said it a couple of times, but I'm in a prize-giving mood. So first one to write that in as Jamie finds his way back to the slide he was on. GREAT terminal. It's going to be a tough one for anybody not from Victoria, not used in other jurisdictions very much. But we'll let you keep going. Oh, here we go. Gating redirective energy absorbing terminal is correct. Adoyle has got in there. I'll check that as to a username, but yes, gating redirective energy absorbing terminal. Thanks, Jamie.
So again, if you're in Victoria, be mindful that this drawing is not up to date. I expect there's a revision in the pipeline, and I encourage you to look to the new version of Part 6. So as I say, the run-out length method looks to provide a barrier that's long enough to prevent that vehicle from getting in behind it and ending up striking the hazard, which might be a creek or a river extending across here. And you can see here by the tyre tracks what's happened. An errant vehicle has left the road and not been able to pull up in time before it's ended up in the drink. There is a barrier up here shielding the worst part of the embankment, but if that was designed based on the run-out length method, you would have seen the barrier extend quite some distance down the hill to shield vehicles from the river and the pole and the tree and everything else that you can see there. At rivers, it is commonly the case that a very minimal or token length of barrier is installed. Here you can see a barrier on the structure itself, and then basically, we've basically just got a terminal off the barrier, or perhaps one rail of guard fence plus a terminal. That certainly hasn't been designed in accordance with the run out length method, which would have seen the barrier extend quite some distance up the road and hopefully prevented this vehicle from getting to that tree or the river. The alternative method is the angle of departure method. So in that case, we assume that vehicles will depart the road at a fixed angle. So in high-speed environments, you can see there it's 2.9 degrees, which is a bit of a funny number. The easier number to work with is this 1 in 20 run-out gradient. So that's sort of 1 laterally to 20 longitudinally. So if you're looking to work out some barrier lengths, you can draw some triangles using that run-out gradient to work out how long a barrier needs to be. The angle of departure method typically results in some longer lengths than the run-out length method. So from that point of view, I suppose it's more conservative. The other thing that the angle of departure method results in is the same length of barrier on the approach to a hazard as on the departure side. So the same length of barrier for this vehicle in the adjacent lane travelling towards this hazard as for this vehicle in the opposing lane. So the barrier is basically mirrored about the centre of the hazard. Now this drawing is misleading, it doesn't show it that way. It looks like we've got a different angle here to here, but you can see they're both at angle A. So we have some really long lengths of barrier or seemingly long lengths of barrier on the departure side of the hazard, or the side that could be struck by the vehicle in the far lane. In a one-way situation, we adopt our run-out angle A here to determine how long our barrier needs to extend prior to the hazard. But we don't need to continue that barrier further along here because we haven't got any traffic going the other way. In working out where to terminate that barrier, we can use a different angle B, which is our trailing angle. And if I step back to the table, we've got this trailing angle column, and the numbers there are 22 degrees across the board. And that basically says that we don't expect a vehicle to depart the road at any angle greater than 22 degrees, certainly not without significant speed. So we can cut our barrier a little bit short of going all the way to the end of the hazard on that basis. And that's particularly useful where we might have a driveway or some other constraint here that means that we can't extend that barrier too far. A common approach is to continue your barrier right to the very end of the hazard, and then tack your trailing terminal onto the end of that, but we probably don't need to go that far. Things are done a little bit differently at curves under both methods. In the case of the run-out length method, we would typically draw a line tangential to the edge line and construct that line from the hazard, or the furthest part of the hazard from the road back to the tangent at the edge line. That's not what's drawn here. Here you can see we've got that extra angle A. So this is the angle of departure way of doing things at curves. We don't draw that tangent. We don't construct our run-out line tangential to the edge line. We construct a straight line on the tangent, and then we construct our run-out line at our angle A relative to that tangent line. A little bit confusing, but in general, I suggest it would suffice to, if you extend your barrier such that it cuts off the tangential run-out line between the traffic lane and the hazard, then your you're adequately shielding your hazard. Barrier offset is probably the step that usually takes up the most of our time and thought when we're designing a barrier installation. We have some desirable numbers in mind. We want to provide enough space between the edge of the traffic lane and our barrier to accommodate a broken down vehicle. And if we can provide 4 metres, that is enough for a vehicle to pull over at the side of the road, and for someone to open a door or perhaps change a tyre if they have to. So 4 metres is our typically our desirable minimum offset. On our freeways and highways, certainly in Victoria, we look to install barriers between 4 and 6 metres typically. The other side of choosing a barrier offset is that we don't want to install a barrier too far from the road, that we allow vehicles to work up some severe impact angles with the barrier. And we don't want to encourage undesirable behaviour on the wide roadside, such as people using the shoulder as an additional lane. And we don't want to open up that possibility of rollover as well. So 4 metres is about that nice balance. We do go up to 6 sometimes, where we have a generous verge width, and we might have some longitudinal services at the edge of the shoulder, and it often does happen on these freeways and highways that we have some services running at about that 4 metre offset. And in those cases, we might choose to locate our barrier beyond those at perhaps a 5 or 6 metre offset. 3 metres is typically considered our minimum offset, and the Austroads Guide does talk about 3 metres, but a better practice, I would suggest, is to provide 4 metres. If you're not providing 4 metres, there are some things that you can do to mitigate the risk, such as providing some refuge bays where it is safe for people to pull over if and when they have to. Obviously, we do install barriers plenty of times at offsets less than 3 metres, and they're referred to as absolute minimum offsets, and typically do require approval. We can go down to as little as 0.6 or 1 metre in constrained locations. And it's not necessarily the end of the world to do that. It really does depend on your situation. If we were to apply an absolute minimum offset to a very long continuous barrier, that would be a very different situation to a short isolated barrier on a low volume rural road. So you need to think about, what does installing that barrier mean for maintenance, for emergency situations. And if you are providing a long length of barrier at a less than desirable offset, think about the things that you can do to mitigate the risk, such as providing refuge bays for people to pull over in emergency situations.
Amy, I might just clarify something to everybody. The Jamie presented 2 methods for working out how long your barrier should be: the angle of departure method and the run out length method. The run out length method is the one that's used in Victoria and Queensland. Is that right, Jamie? Do you know off the top of your head?
I think so. Yeah. I'm not 100%, but I think so.
And South Australia even. So the other method, that was the angle of departure method, is the one in New South Wales. And so Jamie added a couple of slides there. So in the slides on your memory stick or in Moodle, you won't actually have the angle of departure method slides. But what I'll do is just grab those and send them around to everybody, so you're aware. But certainly for the Victorians, the South Australians, the Queenslanders, you've got all the slides you need for your jurisdictions calculations, but just the New South Wales people will need that other one. And it's all in the Austroads guide and the worked examples.
Thanks, Kenya. They are all snips from the Austroads guide. Your relevant state supplement to the Austroads guide will clearly state which of those methods is to be used in your state. So there isn't a choice. You are to use the prescribed method for your particular state. Right, so barrier offset, it is a balancing act. We want to get the barrier as far away from the road as we can to provide space for people to pull over and also to minimise the chance of nuisance impacts. It's often the case that we're driving along and we have a momentary lapse and we cross the edge line. We don't want to result in those events resulting in a barrier strike unnecessarily, but we don't want to locate the barrier so far from the road that we're opening up our impact angles and rollover possibility and so on. So we have these desirable numbers in mind, but then we get out on site and understand what we need to work around, and there are lots of things that might mean that we can't achieve those desirable offsets, or that sort of provide us a limited window perhaps within which to install our barrier. If there's a curb in play, that will influence our location. The location of the batter hinge point, so that's the location at which our verge hinges down to our batter. That is critical in terms of locating our barrier. We can't locate our barrier too close to that hinge point, and how close we can go does vary based on barrier product. Guard fence installations, any W-beam, basically we can locate fairly close if we need to, because those systems don't sort of deflect by as much, essentially. Wire rope systems, we want to provide a greater width of verge behind the barrier, between the barrier and the verge, to provide lateral support to the post footings, but primarily to ensure that at least one set of vehicles of that impact, one set of wheels of that impacting vehicle remain on the verge when it's impacted and the barrier is at full deflection. So that's where that little calculation there comes in. D max, maximum deflection of the system, minus 1.3 meters. That's a little equation we often use. So for instance, if you expected your barrier to deflect by up to 3 meters, take away 1.3, we'd have 1.7 meters, which would be our minimum distance between our barrier and our batter hinge point for a wire rope. The presence of table drains, or basically any change in grade or significant change in grade, might influence where we can locate our barrier. We need to be mindful of shy line offsets. The shy effect being the effect where we as motorists tend to shy away, to shift our vehicles laterally away from objects that are located close to the edge of the road. And we might be looking to flare a barrier. We need to be mindful of the maximum rates at which we do flare those barriers. And flaring is particularly useful where we do have an offset that's less than desirable. We can flare our terminal further away from the road.
Well, Jamie, there's just a couple of questions before you jump onto your next slide there. The question is just wondering if approval is required for less than 3 meters on local roads. If so, is it Vic Roads that approves that?
Yeah, no, look, I think no and no are the answers. There is an approval process for Vic Roads roads, and they offsets of less than 3 metres require approval by, I think it's the regional director. There is a list of sort of requirements, I suppose, things you need to think about if you're looking to adopt an offset of less than 3 metres, and things that you ought to be doing to mitigate the risk of going to that. So maximum lengths at certain offsets, providing refuge bays and so on. So there is an approval process, certainly in Vic Roads.
So yeah, really local roads. In this sense, those signing off the designs and the installation would have to be satisfied that the risk is acceptable, I suppose. Now, there's a follow-up question on that one, but I've got Ton with his hand up, so I'm going to allow to talk. Hopefully you can unmute yourself there, Ton, or unless you've accidentally pressed the hand up button, but you should be able to find unmute and talk to us if that's what you want to do. Well, Ton works that out. If so, the next question was, is speed a factor with barrier offset? E.g., 70 km per hour or less, no barrier offset required. Is speed a factor in that?
Logically, yes. In terms of the available guidance, I don't think speed comes into things, but obviously the faster you're going, the more likely you are to depart the road, for one, and the greater the risk if someone does have to stop within a traffic lane. So it's more desirable to provide space for someone to move clear of traffic. But as far as the available guidance, I don't think there's any distinction between different speeds.
Okay, thank you. And I think it might have been a mistake from Tom there putting the hand up, but we are always welcome people who want to have a chat about something to put your hand up. Click that hand up button, and then I just activate you, and you can then press unmute on yourself and have a chat about the topic. But I'll if you did want to there, Ton, just re-put your hand up, and I'll allow you to unmute yourself again.
So look, it really is a case-by-case thing. We do adopt some very small barrier offsets lots of times. And if it is a local road or your speeds are lower, it's a fairly short length of barrier, it's usually fine, provided that we're designing our barrier in the right way. It's when we're looking at long lengths of barrier at less than desirable offsets that we often get into trouble. And there are plenty of installations out there on especially lower speed roads where we have next to no offset. We might have a curbed carriageway with 2 or 3 lanes in each direction. We might have a barrier at the back of curb on the left-hand side. And that's, these are usually urban situations where there are frequent side roads and opportunities to get off the roadway if we need, and our speeds are lower.
Okay, thanks, Jamie. It's a nice photo for us to have a little pause on, I think. So Ton Boo's just put the hand up again. So if you do want to ask a question, just unmute yourself there and ask us the question. Not sure, maybe you are just having computer issues or something's going wrong there. But I think we're halfway through today's session. I'm going to just pop up a little poll and do the usual, give you 4 minutes to answer the question, have a stretch, fill up your water or whatever you want, and we'll get back into it shortly after that. So here's the poll. We'll check whether you were listening to Jamie's length of need. Remember, this is not one that you get marked on. This is just one for you to answer during the session. You might get similar questions in your quiz at the end of the session. So question is, which of these does not influence the length of need of a barrier protected with flaring, post spacings, barrier offset? Now, I'll just all right, we'll get back into it in 30 seconds. Anybody who hasn't had their vote yet or had a guess at the answer, just feel free to pick one if you want. And we've got everybody has popped in the answer, and most people were on the money there. The length of need is not influenced by the post spacing. That will be the amount it will deflect. So it's that sort of calculation of the coverage there. There you go. Okay, Jamie, I'll hand it back to you. And it's, what's the time now? It's just 3:05, so doing pretty well.
This barrier here obviously is at a very minimal offset of perhaps a few hundred mil. It's on Sydney Road in Melbourne and it keeps being struck. It's a real maintenance burden, this one. It is a wire rope, so every time it is struck, it needs to be attended to. So perhaps the choice of system here wasn't the best. There's not much scope perhaps to have installed that barrier further from the road due to trees and other hazards. Maybe there was, but if that could have been located a bit further away, and perhaps if we went with a more rigid system, we could have, due to the reduced deflection, that would have been a better outcome. I should say that the offsets that we've talked about, they do apply to left-hand sides and medians. However, there isn't the same need typically to provide as big an offset on the median side of a divided road. And that's because most people will choose to pull over to the left. If we do have 3 or more lanes, however, we should be looking to provide the same offsets, 3 to 4 metres on the median side as well. The Vic Roads Road Design notes to do with continuous barriers and narrow flush medians with central barriers provide guidance on offsets to barriers in those situations. So I encourage you to look to those as well for some more guidance. I like to show this photo because it demonstrates the old approach to designing barriers. Not that old, we're only talking perhaps 10 years, if that. And at that time, the preference was to locate barriers as far from the road as possible. That meant, and we were designing those barriers based on clear zone thinking, which meant that we could minimise the amount of barrier that we needed to install. We minimised the likelihood of nuisance impacts as well, but we did open up the possibility of a few things. Rollover before vehicles strike those barriers, impacts at some high angles, and also it resulted in some hazards that were outside the clear zone that was adopted, not being shielded at all. So these days, and in fact, this piece of road has since been treated with continuous barriers, and it's been a bit of a challenge marrying up the two approaches. So this road now is generally fitted with continuous barriers at 3 to 4 metres on both sides. You will note if you look closely that the result of this sort of old approach was that you would end up with some weird and wonderful offsets to barriers. So this one here is at 5.5 metres. This one at 6.1. It might be 5.3, 7.2, blah blah blah. Barriers sort of stepping in and out as you drive along that road, and the offsets were based on working backwards from the location of the hazard, locating those barriers as close to the hazard as possible, subject to the deflection of the barrier. The next consideration in determining a barrier offset is relates to curb and channel. If you do have a curb and channel at the edge of your road, that feature will affect the bumper trajectory of a vehicle that impacts it. So we need to be mindful that we don't locate a barrier where the bumper trajectory is outside of its sort of normal height. So you can see there's some options for locating a barrier a long way from the edge of the road, perhaps at the very back of curb, and maybe somewhere in between. Some references there to some guidance on this, but there has been some more recent work which basically says don't install a barrier at this in-between point. So the preference is to locate your barrier quite some distance beyond the curb, something like 7 metres or more, to take out that effect of the vehicle bouncing up and down, or to locate it as close as practicable to the back of curb to capture the vehicle before it's had a chance to bounce up and down. So those are your two preferred locations, here or here. It's rarely the case where you've got curb that you've got 7 metres or more to play with. If you've got curb, you're probably in a built-up environment. So you've got footpaths and trees and poles and things in the nature strip. Or if you're in a rural environment, you've probably got a curb because you're in a cut, and a cut batter in here somewhere. So you usually don't have much room to play with, and this is where we choose to locate our barrier. This option has been attractive at times where we've sought to achieve that 3 or 4 metre barrier offset. It might be that our edge line's here and we've got a 2 or 3 metre sealed shoulder. We want to get the barrier sort of 4 metres or more from the edge line, so we put it back here at something like 1.5 metres from the back of the curb. Or it might be the case that we had some services near the curb that we were trying to avoid. But going forward, installing a barrier here should be discouraged. You need to think about the offset of the barrier from the batter hinge point for 2 reasons. We need to provide enough solid ground behind the barrier to support the system, provide enough lateral support for the system so that it can contain and redirect the errant vehicle. So in the case of guard fence, any guard fence system, minimum 0.5 metre from the hinge point. We can get closer and install a guard fence even up to the hinge point. That might be a public domain guard fence or a proprietary flexible W-beam system. And each of those proprietary products have been tested under some slightly different configurations. Some of them have tested at the hinge point. If we are doing that though, we need to extend our post length to ensure that the system does have enough lateral support. The other reason, or the other thing that we like to achieve when we're determining our batter hinge point offset is our dynamic deflection. The preferred outcome is to contain all of the deflection of the system, regardless of the system, within this verge area. So we're talking, 1.5 metres, 2 metres plus for flexible systems, which is very rarely achieved in a retrofit, certainly. But that is the desirable thing to do. Where we can't do that, in the case of guard fence, we can get closer and even to the hinge point. In the case of wire rope, we need to provide minimum 1 metre, but also thinking about that D max minus 1.3 metre rule, which is intended to keep one set of wheels of the impacting vehicle on this verge. I hope this video is coming through for you all. I'll play it again. It does demonstrate that barriers can and do work when they're located very close to hinge points or even vertical drops, as you could see there. That vehicle was clearly contained and redirected without ending up in the channel. There are requirements for, in terms of slope gradients, maximum allowable slopes that barriers can be installed on. 10:1 is our preferred maximum batter slope for installing a barrier. If we have a 10:1 gradient or flatter, we don't have any trouble whatsoever. If we're retrofitting a barrier, we ought to ensure and undertake grading or earthworks as required to achieve that 10:1 slope in front of the barrier and within that verge area behind and up to the hinge point. There is another situation mentioned in the Ostroads guide. You can see this dashed line here where we've got a batter slope of 5:1 or 6:1 or something in that order. It has said, that's okay if we provide a relatively flat pad in front of the barrier of 10:1. I discourage the use of that treatment. The result of doing this would be that our barrier would be really quite some distance from the edge of the road. there is another requirement to be mindful of where we have slopes in the order of 5:1, 6:1. And that's to do with proximity of batters to hinge points. And it comes from AASHTO, which says don't locate a barrier within, I think, 3.6 metres of the hinge point where you've got a slope of 6:1 or steeper. And that's all about vehicle trajectories as the vehicle sort of goes over that hinge point and the bumper rides up. So to achieve this bottom situation, we'd be looking at offsets, you know, in the order of 8-10 metres or something like that, which is not something that would be desirable. A much better situation would be to locate your barrier up on the verge here. Another video, and this vehicle obviously has penetrated that barrier. I wonder why. This view shows it a bit better. We've got a table drain there with a barrier located just sort of beyond the invert or perhaps a metre behind the drain. If we look again, you'll see that when the vehicle passes through the drain, the bumper height goes down as the suspension kicks in and the vehicle noses under the system. So the moral is don't locate your barrier in close proximity to any change in grade, be it a table drain or a curb or a hinge point that will affect the vehicle's bumper height. The safest thing to do is to locate the barrier in front of any of those features to take them out of play. Barrier deflection. Designers need to be across the amounts by which the different barrier systems deflect, and it is an important consideration in selecting your barrier offset. So your deflection, dynamic deflection, is simply the amount by which the barrier will deflect horizontally when it's struck by an errant vehicle. And the values that we used are based on crash-tested conditions, so really quite severe impacts. We're talking for the MASH TL3, 100 kilometres per hour at a 25-degree impact angle, so it's a pretty severe impact, very high energy. In practice, most impacts are at shallower angles and involve less energy, so we're designing to that sort of that high-end energy strike. Rigid barriers don't deflect by anything or next to nothing. Guard fence systems, public domain systems anyway, can be expected to deflect by up to about 1 metre. We can reduce that by stiffening up the system with reduced post spacings. We can reduce the deflection to about 0.5 metre. Now keep in mind that these systems are no longer favoured. They are, on the most part, considered legacy products. And that is because now that they've been tested to MASH, they don't stack up. So they're either considered legacy products or their use has been downgraded or restricted to lower speed environments, perhaps up to 70 kilometres per hour, which would be a TL2 situation. Flexible W-beam products deflect by in the order of 1.6 metres. That's at standard post spacings. You can reduce the post spacings for those systems. And for at least some of the products, the suppliers have crash tested those configurations. I can't recall if they publish the numbers around that in their documentation, but if they don't, you certainly can contact them and they can give you some advice around how much their systems might be expected to deflect with a 1 metre post spacing, for instance. They can even advise a maximum expected deflection for a specific situation. If you can tell them your cross-section details and where you're proposing to install the barrier in relation to the road, they can determine some sort of maximum expected run-out angles and corresponding deflection. So I do encourage you to contact your suppliers if you're in a constrained situation and you can't afford the standard deflection. Wire rope deflects by even more. Each of the products deflects by a different amount. And that's because they have different post spacings and also because they're being crash tested to different levels. One of the accepted wire rope products is a test level 4 product. And under test level 4 conditions, it deflects by more because we're looking to contain that small truck. So be mindful of that when you're comparing the different wire rope products. You're not comparing apples to apples. But suffice to say, they all deflect by a lot and perhaps by as much as 4 meters or more. Deflection of wire rope systems does increase with the length of the system. The longer a barrier is, the more it can be expected to deflect. The crash tested lengths are not great. They're sort of 150 meters or thereabouts. If you've got a 1 kilometer length, you'd expect that system to deflect by more. The road curvature can also mean that your barrier might deflect by more. If you have a barrier located on the inside of a curve, so the vehicle's going to strike it on the convex side of the curve, the tension in the system's looking to sort of pull the barrier in when it's struck. So those systems will deflect by more again, in all likelihood. There's an example where our deflection obviously hasn't been provided. We might have a few 100 mil available there. It does look like they've tried to stiffen up the system with some closer post spacings, but being a wire rope, that's going to deflect by quite a bit. If struck, probably a guard fence would have been a better outcome in this environment. It is a built-up environment where our speeds are not going to be great, so we're not going to see those full crash-tested deflections in any case, but even still, that pole could easily be struck if a vehicle struck that barrier first, as could that asset. And this pole, obviously, it's nearly touching the barrier. It's a power pole. You probably haven't got a hope in hell of relocating or undergrounding it. It's simply too costly. So in many cases, we just have to do the best we can by stiffening up the system. And you can see that in this case, it's a tri-beam system. So it is a stiffer system. We are on the inside of a curve. Our shoulder width isn't great. So, if we're pushing the barrier further away from the pole, we're compromising that shoulder width further. You can't see it from the photo, but there are other hazards upstream of this pole that are adequately shielded. So whilst we're not providing our dynamic deflection, I would argue that barrier is better than doing nothing. So I guess don't get too hung up on not achieving every desirable parameter when it comes to barrier design. Take all the steps that you can to minimize deflection, choose the product that best suits the site and so on. Document any non-conformances, but yeah, don't be deterred from putting a barrier in if you think it is going to provide some benefit still. Each barrier system has a minimum length requirement, and it does vary between the different categories of product. These are all spelt out on the in the TCU documents or the detail sheets, which can be found at your respective department's websites. For wire ropes, we're looking at 160, 180 metres. Now, I'll note that all of these distances exclude terminals, so you need to add something like 25 metres, 30 metres to these lengths to account for terminals. So for wire rope, we're talking about 200 metres roughly, flexible W-beam around 100, W-beam, it's sort of 30 minimum, and concrete again, it's 80 or 90, something like that. So these minimum lengths can be quite prohibitive, and they can steer you towards certain types of systems, and in particular wire rope can be difficult to achieve. There are plenty of cases where we simply can't achieve the nominated minimum length. And if that's the case, we need to do a bit of thinking about our particular site and what that might mean. If we're only just falling short, it might not be the end of the world. If our speeds are not particularly great, if they're not in the order of 100 k's per hour as per the crash tested requirements, providing a lesser length might not be an issue. So all of these lengths are based on the crash tested configuration, 100 k's, 25-degree impact angle. So if you can demonstrate that your impact conditions aren't likely to be that severe, you may well justify not providing these lengths. Again, I often see that some pretty token lengths of barriers are installed at things like this stock underpass or other sort of small structures. Here we've got a grate on the approach side, a trailing terminal on the other side. Now that would have been designed based on clear zone thinking. It would have been considered outside the clear zone for one direction of travel. We're not thinking that way anymore, so you would hope to see a grate on both ends. It hasn't been designed based on the run-out length method or angle of departure method. If it had been, you would see that the barrier would extend quite a distance further in each direction. And it certainly doesn't meet the minimum length requirements for a barrier. We should look to provide run-out areas wherever we can. Now, I think Evan spoke about these the other day. A run-out area is a nice, sort of relatively flat and hazard-free area that we like to provide at the start of a barrier system. It measures 6 metres wide by 18 metres long from the point of need. Now, this applies to guard fence products and wire rope. And if we're providing a run-out area like this, a vehicle that just misses the start of the terminal, has a sort of a clear run-out path, a vehicle that strikes this gating portion of the terminal and continues through will likely come to a stop within that area. So it is desirable to provide these sort of relatively flat grades and ensure that this area is free of hazards. That may influence where you start and stop a barrier. You might choose to extend the barrier a little bit further to ensure that it starts in an area that provides a better run-out area. Now, any barrier must have an appropriate end treatment that serves two purposes. It needs to ensure a crash-worthy outcome when a vehicle strikes end-on. On the left, we have a grate. That's the ETSS system, one of the new MASH-tested products. So if a vehicle strikes it, it'll, in theory, bring the vehicle to a controlled stop over a distance of about 15 metres. On the right, we have a wire rope system that won't bring the vehicle to a stop, but should not cause the vehicle to to roll as it passes over. So they have you can see there a fairly, a very gentle increase in height. These systems are about 12 metres long, the currently accepted crop of products. The other function of the system is to provide anchorage. Now, flexible W-beam products and wire ropes work predominantly by the tension developed in the system through the rail or the cable. The posts do offer some lateral support. The tension is the main mechanism, so having a sound anchor point at either end is critical. We've already gone through what GREAT stands for, Gating Redirective Energy Absorbing Terminal, and there is one of the other newer MASH products. That's the MSKT. So when struck, it's an extruding type terminal. It's going to spit the rail out to the side. So that's another reason why it's nice to provide a run out area, so that when that rail is extruded, it can operate free of any objects that might be located behind the barrier. If we have a break in a barrier, or we need to sort of work with two different types of systems, we need to transition them somehow. And transition can be done directly in some cases where we connect two different systems together, or the other option is to overlap the two systems. And here you can see an overlap. And I want to point out that vehicle is facing the wrong way. This is a one-way carriageway that's not yet open to traffic, but when it was open, traffic would be travelling towards us.
I was trying to draw on it there, Jamie. I think I've made things worse. There we go. There's an arrow. Did it come up?
Yes.
That's direction of travel.
So direction of travel towards us. The desirable thing when overlapping barriers is to overlap our points of need, our points of redirection. And if we're doing that, there's no opportunity for an errant vehicle to pass through a gap and into the roadside. With this guard fence, we've got a 10-metre long gating terminal, a breakaway cable terminal. You can see the timber posts there that are intended to break away. So our point of redirection is here. With the wire rope, our point of redirection is going to be about here at this second post. So there is a slight opportunity there for a vehicle to pass through and into the roadside. So we should try and do better and overlap those points of need. Obviously, there's a very steep embankment there, so to achieve that overlap would have meant a fair bit more earthworks. Another thing to be mindful of when overlapping systems is the distance between the overlapping systems. These two are obviously pretty close together. We should be providing a distance between them that is equal to or greater than the expected deflection of the upstream system. So if you had a wire rope in front of a guard fence, you might be looking at sort of perhaps 2 metres or thereabouts. Now, there is an argument that you're unlikely to see a deflection in that order so close to the anchor point, and that's probably true. But the conservative way to do this would be to locate this guard fence at least beyond the deflection area of this wire rope in front. You can see that we have got a grate on the guard fence, and I think that was done sort of in recognition of the fact that it was probably closer to the wire rope than it perhaps should have been. And it's hard to appreciate from the photo, but the embankment there really is quite steep. So to have achieved a greater offset would have been a challenge. The good thing about this one is the points of need are overlapped, however. There's a direct transition between a guard fence and a concrete barrier on a bridge approach. So where we are directly transitioning barriers, we need to be mindful of the sort of the relative stiffness of the two systems and try and ensure that the stiffness of the two is sort of fairly comparable at the interface between the two. So where we transition a guard fence to a concrete barrier, we look to stiffen it up. And we do that with reduced post spacings, and you can see some posts there at perhaps 0.5 metre, then 1 metre, then it probably goes to 2 or 2.5 metres off to the left of screen. There's probably also a double nested rail, so 2 rails, one on top of each other. And the effect of all of that is to stiffen up this guard fence before it meets the concrete barrier. Now, if it hadn't been stiffened up and a vehicle impacted that guard fence in advance of the concrete, it would deflect, and there'd be a risk that that vehicle would then, the barrier would sort of pocket at this point, and the vehicle might snag on the end of that concrete system. Now, this is a Victorian example. In New South Wales and some other states, the standard arrangement is to use a thry beam, and there is a typical detail in each state on how best to go about this. So a few parting tips. Really familiarise yourselves with the different barrier systems and be aware of their ins and outs in terms of lengths, what they can connect to, footing details, deflections, and so on. If a barrier looks too short, it probably is too short, or it probably doesn't meet the minimum length requirements, which, as you've seen, are quite onerous. A preferable outcome is always to provide a longer section of barrier as opposed to a succession of short barriers, which means more terminals, which are the riskiest or most dangerous part of a barrier. And perhaps, lots of short barriers might even be a more expensive solution than one long barrier, even though you haven't got as much total length of barrier because the terminals are so much more expensive. Flaring of barriers really is an underutilised thing. It's especially important where your barrier offset is not what it should be or you'd like it to be. So if a barrier is within 3 metres of the road, you really should flare it if you can. So by flaring, you're getting it outside the shy line offset and eliminating or minimising shy effects. If you can get it beyond 3 metres, you're probably not going to have any issues with sight distance with vehicles entering from side roads or driveways. If you've got that 3 metre offset or more, you'll find that the entering vehicle can sort of prop at a point where the motorist can see in front of the barrier. Flaring barriers in constrained situations provides better shielding of hazards. It provides you with the sort of most effective barrier in terms of shielding that hazard. Provide run out areas wherever you can, and really do think about everything else that's happening at the roadside. You can't gather enough information on site and through other means before you start designing a barrier. So get out there and think about all those pieces of roadside furniture that might be impacted or need to be relocated. Do a dial before you dig. Be mindful of services before you get out there, and then look for the telltale signs when you're out there. Take all the measurements that you can, particularly hinge point offsets, batter slopes. Think about the sort of window within which you might be able to install a barrier, and what is the scope to do further earthworks if you decide that is something you might want to do. There are lots more things that you need to be mindful of. Sometimes it really does depend on your specific situation. I won't go into any of these now, but if you have any questions on any of these, please raise them tomorrow. I'll hand over to Ken now, being mindful of time, to talk about motorcycle stuff.
Thanks, Jamie. And it's not actually tomorrow; it's on Thursday that they can do that. But if they did have random questions they wanted to ask you tomorrow, I'm sure they could hunt you down. But we're on back on Thursday. Thanks, Jamie. And you can see there, Jamie's covered a huge amount in that presentation. A lot of technical detail there, little intricacies associated with it. So please do pop the questions in now. Think of them and raise them on Thursday, or email them through in between, and we can talk through those. We've got a couple of topics that people want a bit more discussion on Thursday, so we'll do those, and anything else that comes in. And we do love those live examples as well, where you're grappling with a specific challenge. So I'm just going to share my screen here. Hopefully this will work. Yep, you'll be seeing my Zoom, which is not what I want you to see, and I'll just swap that, and hopefully that's right. And Jamie, that's looking all right?
That's good. Yep.
All right. I just want to cover off on motorcyclists and barrier systems, and it's I'll do it in a fairly brief manner. This is something I could talk for quite a long time on, but I just want to touch on a few of the key points so you've got that in your mind and what can be done. And the first thing I think it's important to note is the amount of trauma happening with motorcyclists striking barrier systems. This is some research that was done in Transport for New South Wales originally, but it was out of the University of New South Wales. But it shows there that we have motorcycle fatal crashes, and we see that barrier systems are really a small percentage, very small percentage of this. There's a fair bit of unknown there actually, which is the police reported not knowing what was actually struck that caused the fatality. So it's a very small percentage involving barrier systems. Nonetheless, something we do need to think about. If you drill then into, well, what type of barriers were being struck when these fatal, this is actually an expanded bit of a study, fatal and serious injury crashes happened. And you see there, overwhelming dominance are guardrail systems. Then we've got concrete, tiny bit of wire rope, unknown barrier system. So maybe just in the chat, first person to pop in there what they think the biggest influence on the fact that guardrail is the one that pops out at the top, and I might give out another prize. Okay, we've got lots of there. So we've got ones that I'm going to go with Nathan here. Not to say that the others aren't definite factors, but Nathan's put in there used the most. So I'm just going to jot that down so I don't forget. To give Nathan a prize. Yeah, it's just the most, there's the most of it out there, but it's also the curves. So those who said the curves as well, and the corners, you're probably worthy of a prize, but there were quite a few that came in pretty quickly. So I'm going to give that to just the most of it out there. But the curves is a really important part. You saw that there was a minimum radius of 200 for a wire rope system. That's basically, if you're looking down on it, that's your system. If you had a wire rope of that, you had a terminal and terminal, and you tensioned it up, tension and tension and tension and tension, and it's just going to pull the posts and it'll try to go into the middle of the road. So that's why we don't do it. So yeah, it's not out there on those touring routes as well. So certainly some really good points in there about the curves. So that's, I think, interesting for us to note. There's been some studies and some programs that have done retrofit with barrier protection devices and the like for motorcyclists on popular motorcycle routes, and they've actually shown to be quite successful. So we can get some trauma reduction benefit for motorcyclists with retrofitting things to our barriers or choices of barrier systems. In terms of where the fatal blows are happening in a number of areas, but the thorax seems to be the main one. It's probably the biggest area to be struck. The head also up there as well. But we don't need to go into that detail. But let me take you through and show you some videos to explain this. But when motorcyclists crash with barriers, half of the motorcyclists are on the ground and they're sliding and they hit the base of the barrier. The other half are upright-ish and go over the top of the barrier. So let me show you some videos, some live videos and some crash videos. The live ones have no injuries. So here's one, and you see the motorcyclist goes over the top of the barrier system. So trying to stay on the bike in an upright position and over the top of the barrier system. Here it is with a crash test. And you can see there, that's a dummy, crash test dummy. And you can see that what the bike is doing is exactly what the barrier is designed to do. Deflect, run it along it, energy dissipated. What we're trying to protect went over the top though. The other half of the crashes basically with barriers are the rider's off the bike, slides, hits the base. So fairly low speed, friendly one here, but you could imagine at 80 kilometers an hour, 60, 70 kilometers an hour, that can be a very severe incident. And if, if you have a perception that potentially, that the bike may do some protecting of the rider somehow, it seems to be in some modeling and some other things that shows that the rider is going to separate from the bike and most likely find a post. So another crash test dummy there. And you can see there that that's a weak post system. That didn't really budge when the weight of the human body hit it. Breaks off with the weight of the bike, one of them, and obviously with cars. But the strength of the weak post systems is certainly enough to kill a motorcyclist. So no prizes for saying what could be done for the system for the underrun at least. We know that some sort of barrier underrun protection. I'll use that general term, underrun protection. Some people want to say rub rail. Rub rail is one of the products. I mean, it's the public domain product, but underrun protection covers off all your proprietary products and other things that can be put there as well. So you could imagine a rider sliding along here at 80 kilometers per hour. It's going to be highly severe hitting one of those posts. If we put the underrun protection, they'll hit that and slide along it, hopefully dissipate some energy. And so the public domain can easily be fitted to existing barrier systems, retrofitted. You can see the little brackets that sit it out flush with the front of the barriers. You've got to add those in, and then you put your system there. It's important to note this. That's our end terminal. It's an ET 2000 Plus, I think. So not one of the MASH ones, but it doesn't have the underrun protection on it. Now, the reason for that is that we don't, nobody's tested an end terminal with an underrun protection attached to it, and it hasn't passed the test. So we don't know how it would function. It could potentially compromise the functioning of that very intricate system in its own right. So you don't add the underrun protection to the end terminal. You need to probably factor that into your thinking. There is something that can be done, and this is only accepted for use or for trial in Victoria. Actually, it's a plastic product that sits. It's not connected to the system. It just sits in front of it. And so it's deemed that it won't impact on the functioning of the end terminal itself. Again, it hasn't been crash tested, but it was taken as a on for trial by the Victorian government, just on the end terminals. The question there is, does underrun protection increase stiffness? Well, to get your underrun protection approved, you need to crash test it, and it needs to pass the criteria of the usual crash test with the vehicle as well. And so it's all checked against that. So it really doesn't. It's a pretty flimsy from that perspective, but for the motorcyclist, it's doing the job. So there you can see underrun onto the terminal there, the X350 terminal. Again, not one of the ones we're using these days, but that's the only product, and it's only in Victoria that you can do that. So the crash test that I'm talking about is they get a crash test dummy, they do some little tweaks to it, usual crash test dummy, but mind you, they cost about $250,000, so they're not cheap. Kit it up in its leathers and then fire it at the post. So one test is at the post, one is between the posts. It's at 60 kilometers per hour. And so when you put your underrun protection, that's why you want between the posts to see if it changes, and it's got to sort of cover that. So here's the one at the post at 60 kilometers per hour. And so that you can see that it destroys the dummy, easily enough force to kill the rider in that situation. So the addition of an underrun protection does a really good job of absorbing some of the energy and then redirecting the energy and moving the body along there. So the proprietary products that have been through this testing and have passed the testing are proven to be something that we should be looking at using, and they can be used on standard Type B or G4 W-beam, or on that corresponding proprietary product. So if it's Ram Shield, you'd use Biker Made. If it's Easy Guard, you'd use MPR is their product. I've got these at the end. For the over-the-top crash, it's a little bit more challenging. We don't have anything great, really. There's some post capping, so there's not sharp tops of posts that can be trialed or used in some jurisdictions, and there's a few other little bits and pieces. The wire rope systems, a question that came in, are the dummies reusable? They are, unless you really smash them like that first one, which was a write-off, but they are reusable generally. The wire rope system. So motorcyclists and wire rope have had quite a history, and you may have heard the motorcycle community jumping up and down about it. And it's often that the public has this impression that wire rope's particularly hazardous for motorcyclists. A few points on this. This barrier is so tiny in the representation of motorcyclist trauma compared to, well, other barriers, but also in the scheme of motorcycle trauma. Now, it's kind of, there was a fatality yesterday in Melbourne with a motorcyclist and a wire rope system. So it's kind of, very front of mind at the moment, but you've got to look overall at the holistic trauma statistics on this. A very, very tiny percentage. The one thing I suppose that the motorcycle community has, which is a very valid point, is that we don't have any really good or tested products to retrofit to this to make it less hazardous. Now, we have in some jurisdictions tried post paddings, so they're kind of like the football goalpost padding. It's not going to be as good as redirecting the energy. You're trying to absorb energy, and it's not as good. And nobody actually has had that tested. And I suspect because the manufacturers know it's not really going to pass. But we don't use this product on those windy touring routes. It's on those straights. There's a lot less of it out there. But that being said, if you are designing a barrier system in an area that has high motorcyclist activity, this is not your barrier of choice. You'd use a flexible W-beam or a weak post system with its corresponding underrun protection would be the optimal outcome. It should never be forgotten that barriers are saving a lot of motorcyclists' lives in terms of stopping vehicles entering other lanes and even helping motorcyclists sometimes as they leave the road. So there's some stats there. So here's sort of one of the attempts, which is this stack cushion or a post protector. There you go, just around the post. As I say, not going to be the most effective thing. There you go. It's expensive too. Those are sort of $50 a unit, $70 a unit by now. I think they were about $45 when we put them in on this bit of road, the South Gippsland Highway. The reason we put them in on that was back in the day, we didn't have a weak post system. So our choice was a wire rope or a back-to-back W-beam system or something like that, or a concrete barrier. We wanted the flexibility of the wire rope system. We had some concerns about motorcycle safety due to the fact that this is the run down to the Motorcycle Grand Prix. It gets a huge amount of motorcyclists, albeit on a few weekends a year, but there's quite a bit of that there. So post-pratting was put in there as something. Nowadays, if we were doing this again, it would be back-to-back flexible W-beam weak post system with underrun protection every time for this scenario. There's some more pictures of it. Now, there's lots of products that emerge out there, but so you really need to go to your jurisdiction's approved list and check it out. I mean, this is a classic one. This is it's called the Basic system. It's a fabric that's stretched over the barrier and pinned down, not approved. Maybe it's approved in South Australia. So I would check that before I say that, but nowhere else is it approved. Flexible delineators are just stock standard these days. Another one to try to protect against the rider that goes over the top to stop the slicing. When we used to use the old metal delineators, there were some slicing issues. Make sure the underrun is fitted properly. Here, somebody's connected it to the post, probably because that's a lot easier to install, but you're going to lose that deflection area. There's also gaps then. And so if there's gaps and a rider's leg or arm can fit through those gaps, it's likely to go there as the rider collides with the barrier. So just check the product sheets and it explains exactly how to fit them. And try to, work around there to get any gaps filled with a bit of dirt or whatever, and think about where it's going to run the rider into. So just covering Victorian products, MPR, which is a proprietary product on Easy Guard systems, Biker Shield on Ram Shield, and actually there's Hyasa as well as just been in the approved list. I've got to update that. But just go to your jurisdictions. Go to the RMS website, get Road Design Note 0604 in Victoria, go to the Queensland one and find it out. Few for trial, the poly buffer. We don't want to see poly buffer. This is that plastic product used along the whole system, just on the terminals, and you've got to tell the central office of Department of Transport that you're doing it. And all the post protectors are still just for trial only. There's also some individual post protectors that are accepted for trial. Again, you just got to alert people if you're wanting to use these so they can keep a log of that. And they got Biker Mate and Impact Protect. New South Wales not so keen on many of these trial products, and I'm not 100% sure what happens in Queensland or South Australia. So as I say, just go to your jurisdiction and it'll be all there. So it's right on 4 o'clock now. So any questions we will have to push over to Thursday, where we've got a bit of time set aside. Make sure you do your quiz. Your quiz is ready to go, and that will be the last assignment. Send in any examples, locations, or anything you want talked about after the brief presentation on Thursday. And we look forward to seeing you a few minutes before 2 o'clock Australian Eastern Standard Daylight Savings Time on Thursday. Thank you. Have a good evening.